Determination of pKa value of weak acid. We are all aware the pKa is the modern technique, modern method to find out the strength of weak acids. We have different examples of weak acids like acetic acid, formic acid, chloroacetic acid. The concept of pKa comes in the K, that is equilibrium constant. Whenever we handle with electrolytes, particularly in the two different forms, strong and weak, strong electrolytes are completely ionized, then we are not having Ka expressions. Weak electrolytes are partially ionized or incompletely ionized, where we have Ka expression. Example, if you take acetic acid is ionizes in the equation form like that, CH3COH plus H3O plus, that is equilibrium with water, gives rise to reversible sign with the CH3CO minus and H plus. See, wherever the acids are weak in nature, they are partially ionized, we have Ka. For that, we can calculate pKa value. The experimental setup is like this. We have a pH meter, digital pH meter that shows the variation in the pH values during the titrations. And we have a water containing beaker where we can keep this electrode. The electrode, what we can put it here in this distilled water for a long time whenever we are not using. As the electrodes, the different types of electrodes we are aware. Electrodes are the very aware about the different types of electrode like platinum electrode or even calamel like that. This particular electrode is an ion selective electrode. This particular electrode is a glass electrode. Glass electrode is used for determining pKa value of weak acid. The principle of glass electrode is as an ion selective electrode. It is selects the particular ion of the interest and of our analyte. See, particularly in the determination of pKa value of weak acid in this experiment, the respond ion is H plus. We are going to this particular electrode which we are using, glass electrode, is response to the H plus ion which is there in the analyte. It is in the form of weak acid. We can take weak acid in the experiment in the different forms like acetic acid, formic acid, chloroacetic acid and all. In this ion selective electrode, glass electrode, in the construction we are aware, it is built with, it is inside built with a silver chloride electrode, and there is a small bulb at the end. There inside a 0.1 molar HCl analyte is there, and a glass membrane is there that responds the particular H plus ion which is responsible in the analyte. So I am taking this beaker. So this beaker containing weak acid, any weak acid, a specific volume like 25 ml I can take. Inside a magnetic bit is there. We have a magnetic stirrer. This magnetic stirrer job is to stir the solution. During our experiment, whatever the alcohol we are using, that is going to mix. This beaker containing no concentration of sodium hydroxide. We can start from some particular value to initial reading, maybe somewhere from 20 or 21, 22, or even we can use a microburette to add 0.5 ml. Throughout the experiment, we are going to add 0.5 normal sodium hydroxide. See, now I am going to keep this particular electrode, there is ion selective electrode inside the weak acid, where I am going to determine its pKa value. So you are all aware and you can be able to see that the magnetic stirrer is to stir the solution. So solution started mixing, and we can take the initial value of the pH 2.15. This 2.15 pH value shows that the analyte, the solution which we have taken inside the beaker is definitely a weak acid. It's an acid. We are all aware the acid is with pH value less than 7. Exactly 7 pH become neutral, and more than 7 pH become basic or alkaline. So now this particular experiment variation in pH, we are going to tabulate it in a tabular column. There in the tabular column, we have first column volume of NaOH, we are going to add 0.5 increment. So one particular fixed value we are going to start. We are going to add, keep on adding 0.5. That is the first column, volume of NaOH to note down. The second column is to note down the pH value. How is the pH variation from the pH meter? We are going to record as pH value. Next, we are going to take delta V. Delta V is fixed. We are planning to add 0.5 ml throughout the experiment. That's why delta V become 0.5 ml fixed value. And final column, we are going to calculate delta pH by delta V. See, delta pH also we can calculate. What is delta pH? This, whenever we are going to add 0.5 ml, so there is an increment in the pH. Previous value we are going to subtract it. We are not going to get delta pH value for zero addition or without any addition of sodium hydroxide. That is the beginning reading. So we will get the delta pH value from 0.5. I will tell you how it is we are going to record it. From 0.5 onwards, for 0.5, for 1, for 1.5, for 2, 2.5, we can be able to get delta pH with the subtracting the previous reading. Once we get the delta pH value for corresponding volume, like 0.5, 1, 1.5, 2, 2.5 like that, and delta V becomes the fixed value as 0.5 ml, we are going to take the ratio delta pH by delta V value for all the delta volumes of NaOH added. That we are going to record it in the graph. Later we will show you how we are going to plot the graph in this calculated basis. See, for 0.5 without adding any sodium hydroxide, the pH value shown by the pH meter is 2.19. You can observe this 2.18 value like this. So now I am going to add 0.5 from this reading. See, we can record the increase in the pH value if I add 0.5. That 2 point something what is earlier, that becomes 3.68. You can notice that. See, once if you add the alkali to that particular weak acid, generally we have taken maybe any one form, there is an increase in the pH slowly, steadily pH increases. So now I am going to add another 0.5. See, like this, if I keep on add 0.5, I am going to record the variation in the pH value. So now the pH value goes to 3.97 like this. See, like this, every addition of 0.5 with the fixed volume of NaOH for the burette keeps on increases the pH value. It goes to 4.33. You can able to read that. So like this, another 0.5 I am going to add. See, if I am going to another 0.5, the pH value goes from 4.3 something to 4.68 like that. See, I am adding another 0.5. It goes to 4.83 pH. See, like this, another 0.5, we are going to get 5.05 like this. So you are recorded pH value from zero volume of NaOH without adding, that is a pH, and every addition of 0.5 ml of NaOH corresponding pH value we are recording. That is very important in this experiment. And we are observed from the beginning, if we keep on adding 0.5 ml NaOH, pH value goes on increases slowly. And like this, if we continue for adding another 0.5, again there is a slow increase in the pH value from 5 point something to 5.37. Say again another 0.5 if you add, it will goes from 5.8 something to 6.02 like this. Up to now, what we are observed, there is a slow, steady, gradual increase in the pH value from the beginning 0 like this. And next, if you add another 0.5, again look at this, another 0.5 of further added, there is a jump in the pH value. Whatever the pH value 5.8, 6 point something is shown by gradual 0.5. The next 0.5 ml of the sodium, I am maintaining adding sodium hydroxide 0.5 ml only from the burette. Like this, up to particular value 4.55 like this, there is a slow increase in the pH value. From there is a sudden jump in the pH value. It goes from 6 to 10 point something. See, what is this particular point is, up to the previous reading before adding this 0.5 ml, the added sodium hydroxide reacts with the acid inside. The acid may be acetic acid, the acid may be formic acid, the acid may be chloroacetic acid. Once the acid, whatever we have taken to determine its pK value with the sodium hydroxide, general tendency of neutralization reaction, salt and water is formed. Suppose if it is acetic acid, sodium acetate salt. If it is formic acid, sodium formate salt is formed, and another products are water, and water is the by side product. Now, why there is a sudden jump in the pH from some value from 6 point something after adding another just 0.5? All the acids what is there in the weak acid form completely neutralizes with the base added. The further 0.5 ml base added brings the sudden jump in the pH from 6 point something to 10. We are not supposed to stop at this particular stage when we are going to get the jump. We have to further increase another 0.5, 3 to 4 times in order to complete our graph which we are going to plot there. So, I am going to continue with another 0.5, 3 to 4 times. See, if I am going to add another 0.5, see, I may get again there is a slow increase in the pH, not any jump like that. The way in which I am going to observe the steady increase, slow increase in the beginning, after the jump also I am going to observe there is a slow increase, small increase in the pH value. So I will continue for 2 more readings, another 0.5. So I am going to get 11 point something, 1 point something, 11.16 like this. And another 1 more reading, another 0.5, I am going to tabulate it as 11.98. And further maybe another last reading as another 0.5 ml, and I will reach to that value. See, this is how we are going to complete this experiment. That is how I am going to record a pH value from beginning 2 point something, 3 point something to slow increase 4 point, 5 point something like that up to 6 gradual slow increase. There is a jump from 6 to 10. After the 10, further I am added 0.5 ml. There is a slow increase in the pH value. One limitation you may be already familiar earlier, maybe studied in the theory, limitation of ion selective electrodes, particularly glass electrode. We should not retain the glass electrode where there is a solution of a beaker containing solution having high alkaline range that affects the glass membrane, which is specially used to construct that particular ion selective electrode. Immediately, I am going to take it from the experimental solution. I will keep that another beaker which is containing just distilled water. So now the alkaline which surrounds the glass membrane, which is in high intense concentration, it will be sprayed out, and we can see the pH meter readings slowly, gradually decreases. The pH value, it means that it starts diluting, and that is the safety variance. See, the next idea is we are in this experiment we are going to use this principle. The principle of experiment what we are using here is there is the neutralization reaction, acid-base reactions, and there is a sudden increase in the pH value. And next, one of the reactions we are going to use the Anderson-Esselbach equation. That Anderson-Esselbach equation you are familiar with electrochemistry earlier in buffer construction now. That Anderson-Esselbach equation is pH is equal to pK plus log salt, square bracket salt, to the square bracket acid. The concept what Anderson-Esselbach equation we use here is, if we are going to plot 2 graphs, one with the tabulated result, I told you already, I mentioned the tabulated result, that is volume of NaOH first column, pH variation is second column, delta pH previous this reading to previous reading in the third column, delta V is the fixed 0.5 ml, and the last column delta pH by delta V. With this 5 column tabulated results, we are going to plot 2 graphs. The first graph, I am going to show the graph along with this result, substituted with this video. The first graph is, we are going to take pH along y-axis and corresponding volume of NaOH added 0.5, 0.5, 0.5 along x-axis. pH you can choose the scale, 1 centimeter convenient. The volume of NaOH added may be 1 centimeter, 1 ml convenient scale. If you plot the pH versus volume of NaOH, we are going to get 2 graphs. Just I am going to show the schematic graphs how it is going to get from the tabulated result. The first graph is, you can able to see that if I am going to plot volume of NaOH along x-axis pH along y-axis, there is a slow increase. We are all noticed that there is a slow increase in the pH. pH slowly increases, and suddenly it should, up to 6 ml of NaOH. There is a sudden jump in the pH that brings this high spike, or this brings this particular height of this curve. And next further showed after the 10 pH value, further 4 more getting added, brings the further increase in the pH. So you look at this graph. This is the first graph we are plotted with this tabulated result I showed on the volume of NaOH. This is the recorded results for demo experiments. That is volume of NaOH 0, 0.5, 1, 1.5, 2, 2.5 we are recorded. Corresponding pH variation is taken here also. And delta pH, I told you where the delta pH starts from 0.5, 4.34 minus 3.7, 1.17 like this. We are recorded delta pH value for all 0.5 addition added. And finally, once we delta pH by delta pH from this column, delta is the fixed volume 0.5. If we divide that one, we are going to delta pH by delta corresponding for all the volumes up to where they are increased. See, first graph we are plotted pH versus volume of NaOH. We are going to get a S-shape sigmoid curve. There, slow increase, sudden jump in pH, and slow increase. One more graph is delta pH by delta V versus volume of NaOH. Whatever the volume of NaOH we are recorded in the x-axis 0.5, 1, 1.5, corresponding delta pH value, delta V value gives you a derivative graph. Small spikes increase, and then there is a bell increase, and then goes down and this. This separate graph in the tabular column, we will submit in this video along with it. And this type of reading, whatever we have tabulated, from the second graph delta pH by delta V value, from the apex of the bell, we are going to draw it perpendicular to x-axis. That volume it will give the sodium hydroxide as equivalence point. The value may varies with experiment to experiment, acid to acid we are going to take for the determination of pKa. We may get 6, we may get 7, we may get 6 point something, 5 point something like that. The value what we get from the x-axis, if we draw a perpendicular from the tip of the apex towards the x-axis, that is called equivalence point, neutralization volume. Whatever the neutralization volume we are going to get, we will make it off of that. Example, I may get neutralization volume 7 from this graph, 7 ml here. I will make it off of that. I will divide that volume by 2, equivalence by 2. That is 7 by 2 become 3.5. That 3.5 I would like to call it as off equivalence volume. See, next, this data we are going to use theoretically determined Anderson-Essenbach equation. It is given in the manual. It is in our practical manual. That is Anderson-Essenbach equation. pH is equal to pKa plus log salt by acid. See, salt by acid. What is the Anderson-Essenbach equation equivalence? Postulates we are assumed that. At off equivalence, whenever the off equivalence is there, the ratio of salt to acid it becomes same. Square bracket salt is also equal to square bracket acid. Once the both numerator and denominators are equal, this term becomes 1. Log base 10 1, it becomes 0. Then at that particular off equivalence time, off equivalence range, our Anderson-Essenbach equation gives pH is equal to pKa value. That pH, that particular time, it becomes pK. How we use that concept here? In the graph, I will show you that. How we use that particular in the graph here. Yes. See, I told you the example, we may get 7 is the equivalence point from my graph, my experiment. I am going to divide it by 2, it becomes 3.5. So this off equivalence 3.5, whatever the value I am going to get off equivalence, I will substitute from the first graph, where I have plotted graph pH versus volume of NaOH. If I am going to search from this x-axis, like this, which is tabulated 1, 1.5, 2, 2.5, 3, 3.5 like this. If I locate that 3.5 as an off equivalence from my second graph, from there I will go upward in a straight line form. I will go by upwards. Where this line goes upwards, and touch the S-shaped curve, sigmoid curve, there immediately if I take a left turn that ends with the pH axis, the corresponding pH value at that particular axis leads to the pKa. So this how, by taking different weak acids, put it in the beaker and immersing the glass electrode and added sodium hydroxide for the burette with the increment of 0.5, 1, 1.5, recording the pH value, tabulated in the tabular columns, plotting two graphs, one graph pH variation along y-axis, volume of NaOH along x-axis in the first graph, the second graph delta pH by delta V, which is tabulated in the last tabular column, corresponding volume of NaOH in the first column in the second graph. The first graph is the kind called S-shaped curve. The second graph is the derivative curve. The derivative curve, tip of the apex, we draw a perpendicular to x-axis that corresponds to equivalence. That equivalence we will make it off, that become off equivalence. We are using the Anderson-Esselbach equation concept, pH is equal to pK plus log salt by acid. We are according to that, at off equivalence, salt concentration is equal to acid. Then both the term becomes equal. When salt is equal to acid concentration, that term becomes 1. Log base 10, 1 becomes 0. At that particular point, that pH becomes pKa. That theoretical concept we are using, and we are bringing that off equivalence value to the first graph. We are taking the first graph off equivalence value from x-axis, and we will go up and extrapolate towards the pH axis. That corresponding pH what we are getting from the graph, that becomes pK. So without much calculation, just plotting two graphs with the tabulated results, we are going to determine pKa value of weak acid against sodium hydroxide as a base taken. Thank you. Thank you.